Hi, and welcome to Tea Leaves Programming. Today we're programming like it's 1979. Haskell for Dilettantes. Today we're going to talk about applicatives. And I'm going to tell you everything you need to know about applicatives, which is that they're really stupid and you shouldn't use them, is what I'd like to say, because I have found the applicative chapter of the System FFP course to be super frustrating. But after thinking about it a little more, I don't think it's applicatives that are the problem. I think it is the course itself. Now, you might be lost right now because you presumably may not even know what an applicative is. And that's also true for everyone taking the course, because my contention is this course is introducing these in the wrong order. Let's talk about functors, applicatives, and for maybe the first time in this course, monads. So these concepts build on each other. And here's my attempt to try and explain these in one sentence, along with their type signatures. So we talked about functors last week, and the way I like to think of functors is with the word mappable. A functor is something that is mappable. More generally, you could say that a functor applies a function inside of some context F. So if we have some A in a context F, and we have a function from A to B, if it's a functor, we can apply A to B to A in that context F and end up with a B in that context F. There's a concept we have not talked about in detail that if you have been on the Haskell train for a while, you've certainly heard the word monad. What is a monad? A monad is a type of functor that sequences computations. So the result of one can influence the next. So we have some monad A, it's living in a context. We have a function that goes from A to a B in some context, and that lets us get back a B in that context. And the key here about these monads is that unlike in a functor, these are actually sequenced. There's some notion of not exactly time, but ordering in a monad. So if you look at these type signatures, they look similar to each other. I've swizzled the order here to make the explanation easier. Applicative comes out of this paper from Connor McBride and Ross Patterson, where they noticed this pattern very similar to the seek optional function that we implemented in the list chapter, where you have a list of functions or some functions in a context, and you have values in a context, and you'd like to apply the functions in that context to the values in that context. And so I've shown these as functor, then monad, then applicative, because that's how those concepts were discovered. That's kind of the order in which those concepts were made into abstractions or widely understood as abstractions. In code terms, an applicative is a functor, and a monad is both an applicative and a functor. So that's why, fundamentally, this course is doing these in this order: functor, applicative, monad. But that's not how the concepts kind of originated. Originally, they were kind of in that order. And this all reminds me of a classic document by a guy named James Aspnes. Has a set of notes on discrete mathematics for his course. Basically, this is the amount of discrete mathematics you need to know if you want to do CS. And it's a great, great paper, and I really suggest you seek it out. It's literally called Notes on Discrete Mathematics by Aspnes. And in one section of the document, he talks about proof techniques. And his number one technique, top of the list, is start working the proof from the beginning to the end. At the same time, start working the proof from the end back to the beginning. And when you meet in the middle, pretend you were working forward from the beginning all along. And that's what introducing applicative before monad feels like to me. So that, I think, is why I've had such trouble with them conceptually. That's all the preamble. Let's actually go on and start doing these exercises now. Right, so here we have our definition for the applicative type class. This functor k double arrow to applicative means that applicative, any class that wants to implement applicative must be a functor. And we can see it defines two functions. One of these functions is called pure, which says given an A, yield an A in a context, the context of whatever is, whatever this applicative is, whatever type is this applicative. And this little kind of TIE fighter like left angle bracket, asterisk, right angle bracket, pronounced apply, which says given a function a to b in some context, and given some A in some context, yield some B in some context. So intuition-wise, this kind of looks a lot like functor, right? So how's this going to be different? I think we have to actually start trying to use it to understand. We're going to start with exactly one. Someone asked me out of band, what's the point of exactly one? Exactly one is not a type class that you would probably ever see in the wild. I think exactly one, its didactic purpose here is to be the simplest type that takes an argument or parameter. It's the simplest parameterized type, right? Literally all it is this container that holds one thing. I don't think there's much use for that in the world. If I'm wrong and really this is some well-known Haskell class that is used all over the place, please leave a message in the comments. I want to learn that. But my sense is this is just about having a kind of simplest possible parameterized class. Okay, so we're going to implement pure and we're going to implement apply for exactly one. So pure, I don't think we have to do anything. I think that is the definition for pure. I think we could also imagine doing this. I guess I shouldn't use two. I'm being bloody minded and not using a backtick because I don't want to. You know, this would be an alternate non-point free version of that. And let's look at our apply. So how do we apply? Well, I'm going to convert this away from point free. We've got some function in a context. So normally I would do that, right? But let's call it context function, just so that I'm remembering that it's in a context. And we've got some exactly one A, right? We'll put a hole in place here. Pure alt is not a visible. Oh, because this is not just a function. This is actually in a class definition. So let me get rid of that. And this just tells us exactly. I got to stop using the word exactly if we're talking about the class, the type exactly one. So let's, as is my wont, deconstruct this a little bit, right? We know this function is in a context. So instead of having this binding context function, let's use pattern matching to deconstruct it. And now we actually have our function a to b. Our a is still inside exactly one. So let's deconstruct that too. Let's call it item. At this point, and I'm going step by step here because we're starting this out. I want to make sure we're all following what's happening here. So now we're still looking for exactly one B. We have an A and we have a function that goes from A to B. That means we can apply that function to that item. And this is a B. We need an exactly one B. We can just feed it. We could use the exactly one constructor and bring it right in. And that compiles. And in fact, I don't know if this is conceptually correct. It certainly will work. We can do that. I want to emphasize that in this particular case, pure is going to bring this item into the context. I never liked the name pure, but I don't know what a better name would be. That would be a great topic for the comments. Of course, we get a bunch of failures because there's lots we haven't implemented, but if we go back here to the beginning, right, and our exactly one tests do pass. One more note about pure. I said I don't like that name. What is pure doing? Pure is taking a value and it's putting it into the context. And what does into mean? Into sounds very container-like, right? People use different terminology for this. The terminology that I've heard a lot and that we're going to see in the rest of this module is lift. Lift a value into a context. We could also say it's wrapping a value in a context. Lift is probably the term you'll see most often. Let's actually try this example here and try and understand what's going on here. So given a function plus 10 in exactly 1, apply it to exactly 1, 8. And what we get is 18. Okay, and presumably that would work with any kind of multiplication, arithmetic, or really any function that's going to work here. Let's just try a different value. So we could not do this with a functor, right? If we tried to use fmap to do this, what do you think is going to happen? You could probably guess it's not going to work. But what do we think is going to happen? What I think is going to happen is we're going to get a type error. And that type error is going to say, I expected this to be a function from A to B, and instead it's a function from A to B wrapped in an F. Let's try it. Okay. Couldn't match expected type, A1 to B, with actual type, exactly 1. But we can do... We could do that with functor. The idea here is that your function, whatever it is, this is kind of a little bit silly because we're typing it at the command line, and why don't I just remove the exactly one? The answer is, for business logic or whatever reason, you already have your functions in this context. And so, sure, you could take them out of the context and then invoke functor, but if you've already got them and they're already in the context, wouldn't it be great to have some function that would apply them? And that's what apply is about, and that's what applicative is about. Let's look at a list. Insert into a list. We need to implement pure and apply for the list type class. For the list type. Listen, I watched my previous video and all over the place I'm confusing type and class and type class, and precision matters to me. And when I watch these things later, I'll go and add subtitles indicating that I recognize that I messed up. But please grant me grace. We are implementing a type class for the list type. All right. So what do we got here? If we have some value A, and we want it to become a list A, or we want to insert it into a list, or lift it into a list. We don't need to worry about the nil case. I don't think you could have the type list. Well, you could have list A. So I think we can just use cons, right? Can we just do this? Is there a reason why that's not correct? Well, we'll find out when we reload it. And then we've got apply. So we've got a list of functions, and we have a list A. Hotel, what? Right, so pure is not correct because I haven't actually... That should do it. There's probably, I'm sure there's a point-free way to do this, and I'm just not going to bother. Okay, so pure is now correct. And here's our standard, very unhelpful, the bindings we've chosen are not very useful. So what do we have to do here with apply? Well, now that we're looking at lists, we have cases where one or both of these arguments might be nil, correct? So what would it mean if our list of functions was nil? We want to apply a list of nil functions to some list of values. So let's say I've got one list, it's nil, 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 nil. We have another list, 2, 3, 4, 5. What would I get back? I would expect, if I'm applying nil, would I get back a list of nils? Or would I get back... Okay, so first of all, I'm totally wrong here. My description was wrong. Because if list A to B is nil, that does not mean that I have a list of nils. It means that I have nil. So I'm applying nil to 2, 3, 4, 5. What does that mean? I think that means nil. I think you cannot do it. I think if I apply the value nil, it's not a function, so it's meaningless. And so I think in that case, we're going to do that. Then what does it mean if we're applying a function to nil? I think it's going to be the same thing. That's what I think. Now we have the case where we actually do have some list in a context, some functions in a list context, and some list of items. All right. And this should look actually exactly the same, I think, modulo my binding names. So we want to apply each function in the list, that sounds a lot like iteration, to each function in the list of items. That sounds a lot like a fold as well. So like a fold within a fold? So one way to do this would be to write an explicitly recursive solution. That's going to get ugly, I think, because we have to recurse both of these lists. On the other hand, it would probably be easiest to explain rather than nesting a bunch of folds. Well, how can we follow the types here? If this were just a function and not a list of functions, we could do that, right? Because we're applying a function to a list of items. The issue here is that we have a whole list of these functions, right? And this isn't going to work. This is going to fail our type check because that's not, right? We have a list of AB. Well, if we got a list, maybe we can use fold right here. Fold right. Something. It's going to end up with a list. it's going to be applied to list of items. No, because what I want to do is I want to apply this to this list, right? We want to go through each function in this list. And so fold right's going to do that for us. And in this hole, what we want is something like x is going to be our function, and then we want to, this isn't going to be right. Let's say, what happens if we append it to that list? Will this actually compile? Kind of match expected type B with actual type list B. Map function to list of items is giving us a list and not a single item, of course. I feel silly. For one thing, I can get rid of the extra parentheses. So this is a list. This is also a list. And I'm trying to do that. I actually want to be appending it, I think. Compiled. All right, we've done it. There is surely a more concise way to do this. But I found this is an example where I think following the types actually worked, right? The thing that gets me about these error messages is they have all the information I need. Like, they're there. It's telling me, it told me exactly what is wrong. They're just formatted so ugly that my eyes have trouble parsing them. It's not a brain thing. It's an eye thing. I don't see it. And I know it's an eye thing because there is a web-based functional programming language called Elm that gives perfectly comprehensible error messages, and most of the difference is simply they're formatted a little more neatly. Makes a difference. All right, let's move on. Actually, before we move on, there is one thing here. Since our implementation here uses fold right should do the right thing with nils. And so I think we can actually get rid of those extra lines and it should work fine. Okay, insert into an optional. In this case, pure, we're going to lift something into an optional. We don't have to worry about the empty case here because we are given an A. And so pure is just going to be full in this case. Or if you were doing this in the maybe monad or the maybe type, you would, the implementation would be the word just. Okay, and now we've got apply. So we have some optional functions and we have an optional A. Optional item. So here we do need, I think, to handle the empty case. Same thing as we did before. If we're applying an empty function, we're going to get empty back. If we're applying a function to an optional that is empty, we're going to get an empty back. And in the remaining case, we've got a full function, and we've got some full item, and we are simply going to sequence this way, and that should be the implementation. I haven't seen these lift functions, but that looks like it works. Passing a bunch of tests, I love it. Insert into a constant function. So here we have some actual, what's going on here? Let's look at the examples. Plus applied to plus 10, and then that whole thing applied to 3. I see, plus is our constant function, and we're applying some value to one side of it. So that's, no, I don't. How is that 16? How is plus apply plus 10, 3, 16? Oh, I see. We're doing the thing where we are applying to the reader. This is one where, I don't know, man. I don't know. I'm going to be riffing here. All right. So the reader is kind of that, right? So given some A, applicative that takes T, given some A, return, I don't know what the wording is here. Return a function that is essentially a partially applied function. Well, let's, wow, what just happened there? Let's use our superpower of putting a hole in place and see if we get any advice here. Okay, so the hole is given an A and a T yield an A. Kind of like ID almost. Valid hole fits include pure, that doesn't help us. Lift 0, that doesn't help us. Const. For all A's and B's, A and B to A, which is T to A, but I think that's fine. Is the implementation here just const? It is. All right. Now this one, oh boy. We're going to follow types on this. T, some function A to B. That's pretty mean. We have no useful hole fits. All right, let's break this down. We have 2 arguments, and we're going to get back this third, right? Our first argument is I'm ignoring this for right now because I don't even know how to describe what that means. All right? I'm just giving it a name. I'm calling it TAB because it looks like TAB. And indeed, that had T to A to B, T to A to B. That's the first argument. Great. So it bound correctly. I don't know why I'm surprised by that, but I kind of am. But now that we're doing that, let's call this one, what do we get? T to A. Found a hole, T to B. We have a function that given a T will return an A, and given a T will return an A to B. So once again, I said this has 2 arguments, but because this is a T implies B, T to B, I can treat it like it has 3 arguments. And indeed, I've got my T here. And now that I have all 3 of these things, now I think I could start doing this. No, I did something wrong. T yields an A to B. This yields an A. Okay. That yields an A to B. That yields an A. That's going to give me a B, which was in fact what we wanted. And just to show you, go back here, right? We know that the last thing to come out of this function was the B. I'm really uncomfortable with this. I got to tell you, of everything we're doing here, this leaves me feeling like, okay, mechanically, I understand that there are permutations here, but this is me being in service of the compiler errors, which I guess is what follow the types mean, but it leaves me a little uncomfortable. Moving on, there's a transition here. So I've been recording for about 40 minutes, give or take. And everything we've done up to this point has been implementing the type classes on various types. Everything after this point is actually writing functions that require those type classes. So I think this is a good place to break. We're going to set this aside. I'm going to read the applicative paper a little more to make sure I really understand what's going on here. And then when we come back next week, we will start implementing our various lift functions. And there's a lot of cool stuff here. Lots of, if you like symbols, if you like unreadable function names that use gnostic glyphs, Haskell has you covered. Thank you for joining me on this journey with Haskell for Dilettantes. Please do like and subscribe. It truly helps the channel. This has been Tea Leaves Programming. We're programming like it's 1979. Thanks for watching.